Hello, everyone. Today we are going to talk about weak instrument and finite sample bias. So here is a summary of potential problems of IV and two-stage least square estimate. First of all, the standard error of IV estimates can be large. In fact, even the point estimates are different. The OLS confidence intervals are often contained in the IV or two-stage least square estimates confidence intervals. The reason that the standard errors of IV are larger intuitively is because we use instrument to pick up some variation and throw out some endogenous variations. So we actually use less variation in the IV estimator. So therefore, we use less information, so the standard error will be larger. Also, the idea of finding the instrument is actually very tricky, right? Because an instrument needs to be strongly correlated with endogenous X. However, the stronger the instrument is correlated with X, the more likely that the instrument is also correlated with the error term. Right. Think about if you use father's education as an instrument for children's education. Obviously, father's education is a strong predictor of children's education, but it is likely to be biased in the same direction or endogenous in the same direction like the children's education. And we were going to show that even a small correlation between the instrument and the error term can lead to large inconsistencies if the instruments are only weakly correlated with X. And also, weak instrument may also lead to poor finite sample property. If you remember, the IV estimator is biased, but it is only consistent when the sample size goes to infinity. There actually is finite sample bias. And we are going to talk about some of the finite sample properties. Okay, so the first thing we are going to talk about is the large estimated standard errors. So it is very straightforward to show that IV and two-stage least square estimators have a large variance than the OLS estimators. Right. In fact, two-stage least square estimator and OLS estimator, they look almost identical, right? The only difference is in OLS we use X. In IV we only use X hat because we use instrument to throw out some endogenous variation. So we only use X hat. Right? And we can actually write X hat as X prime PZX. So what is PZ? PZ is projection matrix, right? And we can show that X prime X minus X prime PZX equals to X prime MZX. And what is MZ? MZ is what we call residual maker matrix. Right, because Y, we can decompose Y into PZY plus NZY. Right, so I identity matrix actually equals PZ projection matrix plus the residual maker matrix. Right, because we know that Y equals Y hat plus Y double dot, the residual, right? So we can decompose anything into the linear projection plus the residual. Okay. And we know that MZ, the residual maker matrix, is positive definite. So that means x prime x is greater than x prime pzx in the matrix sense. So it implies the variance. That implies the asymptotic variance of OLS estimator is actually smaller than the asymptotic variance of the IV estimator. Right? So the difference between the two asymptotic variants actually is negative definite. Right? So the reason is x prime x minus x prime p z x is positive definite, which means x prime x inverse minus x prime pz x inverse is negative definite. Right. But in the scalar case, that just means the variance beta hat OLS is smaller than the variance of beta hat IV. Right? If you only have one variable, then that's become very straightforward. It's going to be just this, the variance of OLS smaller than the variance of IV. And you can apply the same logic to the heteroscedasticity case. Right? So let me repeat again. The intuition is very simple. We use more information in the OLS estimator. So the standard error or variance is smaller for the OLS estimator. We use less variation in the IV estimator because we use instrument to throw out some endogenous variation. That's why we actually use less information to estimate the IV estimator, and that's why the standard error and variance is bigger. Right. So here, intuitively, more variation in explanatory variable implies more variation is used, and so a smaller variance. Right. In two-stage least square, we use x hat instead of x. X hat has less variation than x by construction, right? Because x equals x hat plus r hat, the residual. So of course, there's more information in x than in x hat. Empirically, beta hat IV has larger standard errors and wider confidence intervals than beta hat OLS. So in the figure below, you can see even though beta IV is consistent and beta OLS is inconsistent, the confidence interval is much wider and contains this confidence interval of OLS. So statistically, they are not distinguishable. Look at here. So here, right, obviously, this is probably, let's call beta prime. Right? So beta OLS is centered at beta prime. It's biased, right? So it's actually greater than beta. The confidence interval is much narrower for the OS, and it's actually contained in the IVS confidence interval. So in this case, you cannot really distinguish these two, right? Because even though they have different point estimates, statistically they are the same because the standard errors for the IV estimator is so big. Okay. And in fact, in this case, we may prefer the OLS estimator than the IV estimator. Right? The reason is, well, remember in real world data, we don't observe the whole distribution, right? We only observe one realization, right? So in real world, your beta, hey, IV may be here, right? So the whole distribution, but you may get one realization. Your maybe here, which may be very far away from the true beta, but the OLS you may get around here, because the OLS confidence interval is so narrow. Your beta OLS, your OLS estimate is going to be very close to beta prime, but your IV estimate could be very far away from beta, right? You may get like here or here. They may be very far away from beta, and in that case, the OLS estimates is likely to be better than the IV estimates. Okay. Now we are going to talk about the second problem. The second problem is asymptotic bias or inconsistency. Right, so we say that IV is biased in the finite sample, but it is consistent. So asymptotically, there's no bias. However, that is based on the assumption of IV1, the assumption that the instrument is perfectly exogenous. However, if there's some small endogeneity, let's say the instrument is not perfectly exogenous, but less endogenous than X, can we still say the IV estimator is better than the OLS estimator? Well, the answer is no, not necessarily. So the IV and two-stage least square estimator are not necessarily less biased or less inconsistent, even if Z is less endogenous than X. And it is actually very easy to show from a simple regression model here, right? So if we just look at the simple linear model here, it's very straightforward. So this is the probability limit of OLS, right? It's beta plus whatever the covariance between X and U over variance X, right? And this is the probability limit of the IV estimator, right? So let's say covariance ZU is less than covariance XU. So Z, the instrument, is not perfect, but less endogenous than the X. Can we be sure that the IV estimator actually is less biased or less inconsistent? Can we say this term covariance ZU over covariance ZX is less than covariance X and U over variance X? Can we say this is true? So obviously no. This is not necessarily true because we know covariance ZX is less than variance X. Right. So even if so remember, there's no direct way to test whether an instrument is valid, whether an instrument is perfectly exogenous or not, right? Because we don't observe the error term, so we can't be sure whether the instrument is perfectly uncorrelated with the error term. In many cases, we may be able to argue that at least my instrument is less endogenous than the variable, than the endogenous variable. Okay, but here the results here shows that even if that's the case, that your instrument is less endogenous than your endogenous X, there's no guarantee that the bias from the IV estimator or the asymptotic bias is necessarily less than the asymptotic bias from the OLS. Okay. And because that depends not only how endogenous your instrument compared to the endogenous variable, it also depends on how strong the first stage is compared to variance X. Okay. So if we rewrite the covariance into correlation coefficient, we actually can get this formula here, that we know the asymptotic bias of IV relative to the asymptotic bias of OLS equal to the ratio of the correlation coefficient between Z and U and correlation coefficient between X and U. So this part is how endogenous Z versus X. But also the second part is how strong the first stage, the correlation coefficient between Z and X. Okay, how strong the instrument, how strong the instrument is, how strong the instrument can predict X. For two-stage least square with multiple instruments, the formula is the same. We just replace Z by X head. Right, we just replace Z by X head. And we replace, so this is just covariance XZ. We just replace this by X head, which is variance X head. Right, we just replace Z by X head, then that is variance X head. So the asymptotic bias of two-stage least square estimator relative to the asymptotic bias of the OLS estimator is this guy here. The covariance XU over covariance XU times 1 over the R square, the first stage R square. Right? So that is the R square from regressing X on Z. Okay. Right, if you remember, because variance X head over variance X is R square. Right? It's R square. Right. Just right. So here we have, so this guy here become 1 over R square. If you wanted to be a bit more precise, because the above formula actually indicates inconsistency, asymptotic bias, so we should use probability limit of X head and the population R square. So actually we should probably use X star if you want to be a bit more precise. But you understand what we are talking, right? Basically that's the linear projection. The above results can be generalized to a multiple regression with common exogenous variable, right? Because in most applications, we will have some common exogenous variables, right? For example, we may request earnings on education with control for age, gender, and race, right? So that's empirically we will almost always have some common exogenous variables. So the relevant parameters will be partial R square, which is the R square from the equation of x on z once the common exogenous variables have been partial out of both x and z. Okay, so basically we regression the residual on the residual of x and the residual of z. Okay, and this is just an application of the Frisco-Wong theory. The Frisco-Wong theorem, or we call the partition algebra. Okay. So if you don't know what is Frisco-Wong theorem, that's actually like this. So we know that, let's say y equals beta 1 x1 plus beta 2 x2 plus u. So to get beta 1, hey, let's say you want to get the estimate for beta 1. One way is you can regress y double dot on x1 double dot. Okay. And what is x1 double dot? So x1 double dot is from you regress x1 on x2 and get the residual. And y double dot is you regress y on x2 and get the residual. Then you regress y double dot on x1 double dot, the residuals, then you will get x1 beta 1 head. Okay. Then and the beta 1 head you get will numerically identical to, you just simply regress y on x1 and x2. Okay. And why is this important? Well, so the Frisco-Wong theorem or the partition algebra just tell you what the OLS regression is doing, right? Because if you remember, in undergrades, we talk about how to interpret a regression. Right? We say like beta 1 here, beta 1 is the effects or the association of x1 and y. Let's say beta 1 is the effects of x1 and y holding x2 constant. Right? And how does the regression holding x2 constant? Well, it shows that we actually holding x2 constant because the multiple regression here, when you regress y on x1 and x2, we holding x2 constant because the regression is numerically the same as we regress on the residuals. And the residual, we already partial out any effects of x2 on y and any effects of x2 on x1 double dot. So that's why we can interpret a multiple regression in terms of like, oh, we holding something constant, right? Holding x2 constant because we already partial out the effects of x2. Okay. And here, because we only care, so when we talk about the R square here, we only care about the explanatory power of the excludable instruments. We don't really care about these common exogenous variables, right? These non-excludable instruments. So we want to calculate the partial R square that focus on the explanatory power of excludable instruments, these. So that's why we wanted to partial out the effects or the association of common exogenous variable on X and the common exogenous variable on Z, and get only the residuals, and then we run a regression of X double dot on Z double dot and get the R square. And the partial R square is the effects of executable instruments. The explanatory power of executable instruments on the endogenous variable, holding or partial out all the common exogenous variables. Okay. And why do we care about partial R square? Well, the larger the partial R square, the stronger the first stage, and that means so the stronger the first stage, the less likely that the asymptotic bias of OLS is the asymptotic bias of the two-stage least square or IV estimators are larger than the OLS estimator. Because the relative size of asymptotic bias between two-stage least square versus the OLS also depend on the partial R square. Okay. So in most software, like in Stata, you can ask Stata to calculate the partial R square for you. But if you use R or MATLAB, if you don't use some package, you may need to calculate the partial R square by hand. So you do need to run this partial R regression. So you need to do this Frick-Swan theorem, right? So you needed to say you needed to regress X on let's say those common exogenous variable. Let's call them M, okay, and you needed to get X double dot, the residual, right? So if you also X equals, you will get X head plus X double dot, right? And we keep the X double dot, and you regress Z on M and get Z double dot, right? And you regress X double dot on Z double dot, get the partial R square. So this is important because I do see some people when they do an IV estimation and they want to argue that my instrument is not weak, so they will report R square. But somehow they forget that they need to report partial R square, not just the first stage R square. So sometimes they just report the first stage R square that looks pretty good, but that's because there are a lot of common exogenous variable. Right, so those, but if they look at the partial R square, sometimes the partial R square actually pretty low, right? Because partial R square is how much the instruments, the executable instruments, how much the endogenous variable actually explained by the executable instruments. So the last thing we want to talk about is finite sample bias. So remember, even if we assume that the conditional mean of the error term given the instruments equals 0, the two-stage least square estimator is still biased in the finite sample. The bias only goes away asymptotically, right? So the IV and two-stage least square estimators, they are consistent but never unbiased. And we know that the finite sample bias arises because we don't know the true linear projection here, and we needed to estimate the linear projection. But the estimated linear projection is actually a function of X, And if X is endogenous, that means that pi hat here is also endogenous. And that means the X hat, which is the pi hat, is also correlated with the error term in the finite sample. Right. So some statistician actually shows that in the finite sample, the finite sample bias of two-stage least square estimator over the relative to the OLS finite sample bias relative to the OLS bias is roughly 1 over F, and F is the F statistic for testing the executable instrument in the first stage. Okay, so here is an example, right? Let's see, we have X1, which is endogenous, and Z1 is exogenous. So, and let's say we have Z2 and Z3 as two executable instruments, and this will be your first stage regression. And Z1 is non-executable instrument, Z2 and Z3 are executable instruments. Right. So what is F statistic we need to get? Well, we needed to calculate the F statistic for testing pi 2 and pi 3 equals to 0 jointly. Okay. And that's what we call, and if you remember, well, so if you, and the partial R square, if you want to get the partial R square here, is like you regress xi on z1i, and we get, so xi here and xi here, sorry, xi, okay, so sorry. So xi equals xi here plus xi xi double dot, and you regress z2 I on z1i, so z2i equals z2 here plus z2 double dot. You regress z3 on z1i, so z3i equals z3i here plus z3 double dot. And then you regress x1 double dot on z2 double dot and z3 double dot. You get partial R square. The R square from this regression is the partial R square, and the F statistics from this regression is also the F statistic we need here. Okay. And of course, to get F statistic, you don't really need to do the partial R algebra or the Frick-Wong theorem. But if you are using R, and since you needed to calculate partial R square, and you can also get the partial F statistic at the same time. Otherwise, if you use theta, you just ask the theta to provide you both the partial R state and the F statistic. In practice, we want to F to be at least 10. So if the F statistic is less than 10, that implies the instruments are weak and there are potential substantial finite sample bias. Okay. Okay. So some practice here are some practical hints. First, always show the first stage result. The first stage estimates, partial R square, the partial F statistic. In Stata, you can use the Stata command here, state first stage, after running an IV regression. If you use R or MATLAB, you may need to calculate the partial R square and the partial F statistic. And if you need to do that by hand, then you probably wanted to do the Frick's-Wong theorem here and partial out the common exogenous variable first, and then use the residual to run a regression. Then you can get partial R square and the F statistic. Always show both the OLS and two-stage least square, and also show the results from the reduced form. Like I said, this is important to show the result from the reduced form. You don't want your IV or two-stage least square estimates are statistically significant just because a small first stage, right? If you remember, beta IV is the ratio of reduced form over the first stage, right? If it is possible that the first stage is very tiny, very, very small, so this guy is very big, and that's why it becomes statistically significant. You don't want that, because we already know that small first stage we already know that small first stage is a really big problem, right? A small first stage can create a lot of problem. That implies that that implies the IV is probably pretty weak. Use built-in IV commands in software instead of plug-in methods. Okay, so don't actually regressing Y on X. So that's people did in the past, right? People don't have a good computer and don't have good software, so they an easy way to implement two-stage least square regression, two-stage least square estimation is actually run two-stage. Nowadays, you don't need to do that. And the reason we already show that first, the standard errors are incorrect, right? If you just regress Y on X hat, you needed to fix the standard error. That's just one additional step. The second is more the second reason is more important. The plug-in method is actually generally wrong. It leads to something called forbidden regression. Two-stage least square actually is a special case. In general, the regressing Y on X hat is wrong. So for example, even if you have one additional nonlinear variable x squared, if you use z and z squared as instrument for x and x squared, that will produce consistent estimates. But if you use x hat and x hat square, if you request Y on X hat and X hat square, the estimates are going to be inconsistent. And the reason that X hat, so you can request Y on X hat, is actually a special case, because see, X equals X hat plus R hat, right, the residual, and we know X hat and R hat are orthogonal, but x squared equals x hat squared plus 2x hat R hat plus R hat squared, right? This guy x hat squared is actually not orthogonal to these guys here. Okay. So that's why, in general, you cannot regress y on x hat and x hat square and get consistent estimate. Okay, even in linear regression here, right? So, and in more generally, like in nonlinear model like Probit and Tobit, you should never plug in x hat into nonlinear regression, like into a Probit model. That's always produce bias and inconsistent estimates. When non-executable instruments exist, which is almost always the case in real-world work, in empirical work, like other control variables, using x hat as instrument is generally more efficient than using z as instrument. For example, when the endogenous variable is interact with another control variables, like we have x1, x2, and x1 times x2, and x1 is endogenous. We can use x1 hat times x2 as instrument, not regressing y on x1 hat and x1 hat times x2. That's forbidden regression. But we can use x1 hat and x1 hat times x2 as instrument for x1 and x1 times x2. And in fact, that's going to be more efficient than using z and zx2 as instruments. So similarly, the previous example, we can use x hat and x hat square as instrument for x and x square, than just using z and z square, right? Like here, right? So we can use them as instrument. That actually will be more efficient than use z and z square as instrument. Just don't simply regress y on x hat or x hat square. Okay, don't do forbidden regression. The last thing is there's something called limited information maxima likelihood, LIMO. So there's some research showing that LIMO actually tend to have better finite sample property. So one robustness check you can do if you are running IV regression is, instead of running the IV regression as a two-stage least square, you can run it as a LIMO. In theta, you just tell theta, or instead of two-stage least square, you want to estimate it as a LIMO. In R, I guess there are also packages that you can use. Okay, let's stop here.